So the topic is the hybrid cube database for crystalline organic inorganic hybrid semiconductor materials and their properties. And so evidently my name is Volker BLUM, and I have the advantage, I think, to be in a relative majority here, because Cormac and Corey are also here, and so Duke University is pretty well represented, our department. That's great, except their effort, as you know, AFLO is much larger than what we do. And we'll see why. But without all these people listed down here, that are in various places, and you'll see why in a moment, this talk also wouldn't happen. And so I'm quite grateful for them. And the other people who are instrumental in this is actually NSF. So we are funded by the DEMREF program. And I'm extremely glad that we are. There are 3 codes here because there are actually several universities listed down here. And so, you see, here we are. This is who we are and what the project is about. And so the PIs of this project, which is the DEMREF funded project, that should appear here too. I'm sorry, but you just saw it. There's actually six people working on hybrid organic inorganic perovskites. And so I myself, I try to do theory work, and Yosuke Kanai is a very accomplished theory from UNC, University of North Carolina at Chapel Hill. If you should meet him if you haven't. David Mitzi is one of the leading people in the field of hybrid organic inorganic materials and semiconductors for many applications in general, I think. And so he's at Duke University, and so I'm lucky to work with him. And Wei Yu is an organic chemist at UNC. Keenan Gondokdu is a spectroscopist at North Carolina State. And Frankie So actually is a very accomplished organic semiconductor scientist who also focuses on LED really in our project and organic inorganic hybrids, but he has a very large operation of his own and is very accomplished at this. And so we're lucky to have this team of 6 people, and our goal is actually more than just to create a database. It is to research the materials from the fundamentals. So David synthesizes, Wei synthesizes, try to understand the theory, put this together with spectroscopic characterization, and then go into prototype devices with Frankie to broaden the material space. And in DEMREF, if you know what this is really about exploring material spaces. So that's what we try to do, exploring a new material space. And again, all these people down here are not here because I needed to list them, but because I wanted to. Without them, PhD students, postdocs, other scientists in the project, not much would happen. And so what I'll try to do within the time that I have, and you can stop me at any time, is to outline the motivations for constructing a materials property database specifically for hybrid organic inorganic materials, semiconductors. This is this hybrid cube database, which stands for design, discovery, and dissemination. And in parts why I'm giving this talk is because I'm interested in the dissemination part, because the database was never intended, and also in writing, never intended to be a standalone database that would monopolize this particular, or even try to monopolize this particular material space and go it alone. The idea was always to have this data as open as possible so that we can interoperate with others. And then finally, I'll come to a few use cases if I have time. So hybrid organic inorganics, the important part is actually crystalline. I should have written this here, although I wrote crystal down there. If you're familiar with them, you know what they are. If you're not, then here's an example with a complex organic molecule. So you basically have the luxury here of having a class of semiconductor materials that consists both of inorganic, in this case lead bromide, and organic components. In this case, this is an aminoethyl quartothiophene molecule, so an organic semiconductor molecule that is anchored here. And the key point is that these are crystalline materials. So you can make them with high definition. Right? So you put 2 components together and you get a new functional material. This is David Mitzi's, and this structure here is not invented. So this is not some theorist's figment. David spent a year on learning how to synthesize with this material in 1999, and actually doing Laue diffraction on this. So there's a Laue diffraction pattern for this, and this helped us immensely as theorists because there are 400 atoms in the real unit cell that you need for the simulation. And so with simple structure prediction techniques, or let alone high throughput for something like band structures, you don't get very far in this case yet. And maybe that'll change at some point, but the system sizes are just very large for first principles. And so the collaboration with experimentalists is essential. Now, as you probably will also know if you followed the perovskite literature somewhat, there was this paper here in 2009 that talks about methylammonium lead bromide and methylammonium lead iodide, and says, by the way, they're useful for photovoltaics. And so 3.8% conversion efficiency. In this paper in August 2019 was cited 8,749 times. So that's an enormous amount in this short time, even for our field. And so when you look into more detail in citation reports on these materials, you find that this really set off a run. There's a 4-year lag or so, and then it sets off with an extremely high frequency. And so there's a lot of materials data being published. And that is also what motivated us, of course, to an extent, because we wanted to broaden the space, right? So this is a very small organic molecule, and that's really what drives in large parts the solar cell applications. But the space here itself is much larger, and you see that there are citations back here in the 2000s, and of course they go back to people who did patient, careful work on these materials for other reasons, like David Mitzi and others. And so why would we want a specialized database here? The first thing is that the materials are actually a fairly well-defined class of materials, and that there is a lot of research going on them, but they're complex, right? But if you make them correctly, you can make single crystals, so they're precisely ordered. The second thing is, in my view anyway, that there are unique aspects that there are 2 components. So this isn't just something you can map in PDB, and it's also not something that you can just map as inorganic components where the atoms are placed somewhere. So the fact that you have molecules actually matters for some of the properties, and the fact that you have an inorganic property for a component actually matters. And the third thing I already said is that they're not easily amenable to rapid screening. So either by experiment or by high throughput theory. So making a material takes time. Simulating even relatively simple properties like HSE, spin orbit coupled band structures, which is what we've largely been doing on the theory side, that also takes time. And so then finally, there's the problem that we're trying to grapple with, which is that there's a huge amount of data being produced in this field by lots of experimental groups, also theory groups, but not easily systematized. You have a large volume of literature, but there are still gaps. And more importantly, data is even contradictory. Sometimes for the right reasons, sample character, for instance. But there is, in my view, a need for having basic, well-curated data in this area. So either experimental or computational. And so this is what we set out to do. And so what are we intended to be? So the objective is to have a community resource. So that the data is open and accessible, and we hope to draw in more people who actually put data of their own in here. And we try to have an effort that focuses on carefully collected, curated data. So often this is manual work, and so this deviates from the from many other databases. These could be our own, they could be other contributors or literature. So we have an undergraduate student who's very good, Becca Lau, who was on the first page right now, who's really going through the bodies of work of various people and extracts properties that are useful. And importantly, from the outset, we had said, and we believe in this, that we wanted to be incorporatable and also shareable with any larger interested materials database. And this is a human time problem, but we wanted to get this done. So what it isn't at this point, because this is a manual process, is a large data collection that's geared at uniformity of data. We could do this, but my motivation is more in the spirit of Landolt Bernstein or Springer materials, if you're familiar with those collections, that really focused on curated data that were collected by somebody in painstaking work, trying to map the properties of the actual material under reproducible circumstances, rather than, for instance, having a homogeneous level of theory that could be right for some and could not be right for others, or same for experiment. And it's not supposed to be, as I said before, a standalone database that's intended to supplant other data collection efforts. We are collecting data because there was no such collection out there. And so we hope that we make a useful contribution. So then, this is something that came about, and this connects perhaps to this workshop, I hope. This is something that came about as a byproduct, which is that, of course, we started working on this. And we started working on this, and you have to tell me how much time I have, Gianmarco, just to make sure.
Yeah, I mean, you can go. Let's take another 20 minutes without problem.
Another second?
20.
Oh, that's long. Yeah, that's much longer than I had planned in the original schedule, but that's fine. That'll work. I won't be talking 20 minutes.
If you want to make it shorter, no problem.
Okay, but anybody who has questions, by the way, please also ask me questions. All right. So Zhao Chengdu is an undergraduate student actually, and he walked into my office in his first year saying, "Do you have a project?" And so I didn't know exactly what he was capable of doing, and I said, "Well, we have this, this, and that," and he chose the database. And he actually, for the first year or so of the life of this database, developed this more or less single-handedly, which was to me very surprising. He's extremely talented, and so he got this off the ground as the sort of keystone component, capstone component of an otherwise much larger project himself for the first year. And then Raoul Lasner is a postdoc who's now in the Netherlands at the Netherlands Institute for Space Research. But he got interested in data at some point, and we had a collaboration that helped us a lot with the group of Giulia Galli and Marco Govoni in Chicago, which I'll come to in a moment. Also on data. The intention was to connect what was originally our HybridCube database to their framework, which is called QRESP. So this is a front end for curation and exploration of reproducible scientific papers. It's founded this year. This is really, the QRESP is publication centered. So you basically archive the data in your publication with reproducibility information. In theory, that's what we should all be doing, but it's rarely ever done. Some people do, some don't, but QRESP would allow you to do this. Of course, this would be a perfect place to get the data into the HybridCube database right now, the material centric. So the HybridCube database is material centered. So it tries to work on what is the material and what are the properties. And those properties, by the way, could be experimental and computational, as I said before. And so he took this on and he wrote, so the server itself, originally not the server, the database was written based on the Django web framework, and it's based on SQL, for instance, MariaDB. And importantly, Raoul put in a REST API for access and manipulation of the underlying data sets, and we made this interoperable. And after we'd done this work, actually what we realized is that we now had a software that I wasn't aware so clearly existed as a standalone project, which is a package that a small work group or consortium can use to serve their own data in a fairly unbureaucratic way. So you put this on your on your machine and pull it together, and then you get it to work, and you can serve data on, I don't know, your favorite chalcogenide materials or something like this. And so it's a much broader little software than you could use, and importantly, you can make it interoperable with others. So if you will, you can use this as a tool to create an ecosystem of small databases that are distributed, and you can connect them to the much larger projects. So we call this MAPbla materials design, discovery, dissemination, and we made it available as an open source project in a separate package later, hoping that it would be useful for someone. And so this is done in 2020, and that also defines what the software does and can't do. If nothing else, luckily, thanks to Raoul's hard work, most of the aspects of how to install this software and also how it works are really documented on GitHub and accessible. And so then this is the database itself, and it doesn't look too surprising. It has a relatively humble front page, which essentially says start searching, and has a few pictures of compounds. And it really currently has data for somewhat above 200 compounds, 200 distinct compounds, 30 property types. And you'll find that not all properties are evenly represented. So a lot of it is crystal structure, because that's often what defines the crystal. So that's, you can get this. A number of them are optical spectroscopies, but we're actually working on populating this. So this is really what we're doing. We have band structure calculations where we can afford them, photoluminescence, absorbance, experimental gaps, but there should be much more. And so we're working with a few colleagues to try and get more data in. And so this is a work in progress, but as I said, the materials are complex, right? So this is, I think, the main point, that in many respects, this is manual labor, and we still hope to get there. And so what can you find? You can find actually some things that are useful. So of course you can depict crystal structure. This is not going to come as a revolution to this audience, but nevertheless we can, using a JMOL plugin. Structure parameters, and importantly, we try to record information in our own words, not in terms of the publications that we get information from, if we do. This comes from our own environment here. David Mitzi is a co-author here, but others don't. On synthesis, for instance, experimental details as far as the relevant, the reference, and other metadata, comments, for instance, by the person who put this in, that there are, and we can certainly do more. If you have data sets of our own, we can also mint a DOI for the data sets in principle. And we have a verify button, which is a small but important feature, so a second person can come in and actually verify that the information put in by the first person is correct. And we find this, I personally find this to be extremely important to have this. Well, you can look at this here in more detail. You can look at the synthesis method, for instance, which you can click to hide. So we have something there that says what was done to obtain this particular data. Hopefully that's accurate. So it's a solution process in this case. The method used was X-ray diffraction. Evidently the Shell X software was used and then OLEX was used. And the CIF file is also available at CCTC. But if we have a CIF file in here, then we could check with the authors. Obviously, we don't just copy files from another database without permission. The reference is here. So this is one of our own groups, of course. And then finally, Xiao Chen added this apparently, right? And you can find out when he added this. And you can see that Shishi actually went in later. And those two are the main authors listed on the earlier list, by the way, of people. Shishi went in and verified the data correctness. And so this is a good example, hopefully, and you can mint DOIs, as I said. And then you can do more. For instance, you can scan the photoluminescence data from the experimental paper and make them available both as data and as a plot. You can take a band structure calculation. The band structure in this case, it consists of organic and inorganic materials. And if you know what you're looking at, then you find that these are very dispersive bands at the band edges. And so this is actually a material with band edges contributed by the inorganic, and the organic basically acts as a spacer material with some dielectric function. So you can learn something from that. You can also download it. And this should be calculated at the level of hybrid density functional theory. So our other work indicates that there is some trustworthiness to the band alignments that we actually calculate. Very good. You can do this for more materials. Let's see, what have we here? For materials where you just theoretically, so this material actually doesn't exist experimentally. You just theoretically put in a molecule based on plausible positions from X-ray diffraction and look at the evolution of band structures. And so we did this because this was actually the starting point for us to research these things, to find out if we could systematically predict trends in some agreement with experiment, and it turns out we can. And so we have this data in here. Of course, we try to get more. Then there's the purely experimental data. One thing I said initially is that there's a lot of data out there, but you don't know how good it is. Right? And this is in fact true even for MAPbla, which is most likely the best studied organic inorganic hybrid perovskite on the planet at this point. It has three phases, orthorhombic, tetragonal, and cubic. But if you focus on this orthorhombic tetragonal phase transition, for which the temperature should be well known, it turns out it is. Many people have measured this. And so this is over the years, the phase transition temperatures that we have in the database. And if you just plot these phase transition temperatures, and all of them were measured for good reasons. If you plot these, you find a large scatter. And so this is already separated out into sample types. And you can see that the sample type has a lot to do with what happens. So the thin film data are outliers, and they're the relatively new data. In the 80s, you can argue that perhaps these were people doing more careful work, or perhaps they were such a small community that they all read each other's papers. And so that's why they focused, why they all fell into the same range, right? Because they all knew each other's work. Could be, could not be, but we can map this and say, what is the state, right? And so this is useful for us. And so we can actually see that the powder data occupy the highest range of the phase transition temperatures measured. The powder, the single crystal is here. This got moved. Apologize. I don't know why the axis label switched lines. It should not have, but it did. But anyway, this is powder, this is single crystal, this is thin film. And so we can extract data like this. And this is already the summary of what I wanted to say. There's more data, of course, and we're trying to grow this, but my main interest is also in the discussions. I was there for this morning, and so I was only, unfortunately, there for a very short part. I apologize. But these are, of course, the things we also need to think about in this context. So what is a material? So what constitutes a material versus, say, a composite or something undefined, right? How do we define what is a material? That's pretty important. And how do we define with specificity what is a given property? So the fundamental gap versus the absorption gap versus the gap extracted from reflection measurements versus the gap extracted from photoluminescence. All of them are different. And then our theoretical band gaps are also different. And so we should record this, right? But this becomes a little bit tricky because you have to have taken a class in advanced solid state physics in order to understand the differences. And not many material scientists have necessarily. And so these are issues I think that came up this morning also in different ways. And so I'm quite interested in learning this. Thank you for listening to this and having me. Thanks.